Welcome back to our MSc Physics class. Today in lecture 13 we have reached a very important milestone in our course on molecular spectroscopy. If you look at the screen, I have displayed syllabus of our unit again. This is intentional because we have now officially completed the first major half of this unit, UV visible and absorption spectroscopy. Before moving forward, today's lectures serves as a synthesis session. Our goal is to connect everything we have learned so far and build a conceptual bridge toward the new physical phenomena we are about to explore. Over the past 12 lectures, we have systematically analyzed how matter interacts with light during absorption. We have studied in detail how molecules and solid-state systems capture photons. We began with optical absorption mechanism. You examined free charge carrier absorption and optical transitions between energy bands. At this stage, you should now be comfortable distinguishing between direct bandgap transitions and indirect bandgap transitions, both mathematically and conceptually. You also understand the role of excitons and how they modify the absorption edge near the bandgap. Next, we established the quantitative foundation of spectroscopy. We derived Beer's law and analyzed it, not just as a formula but as a physical approximation. More importantly, we discussed its limitations as experimental physicists. Recognizing when a law fails is just as important as knowing when it works. From theory, we moved into instrumentation. We dissected the internal architecture of spectrometers. You learned the purpose of light sources, monochromators, sample cells, detectors and signal processing units. We compared single beam and double beam spectrophotometers and understood why engineering design directly influences experimental accuracy. After instrumentation, we explored environmental effects. We discovered that molecules do not exist in isolation. Their surroundings actively modify quantum mechanical energy levels. You learn how solvents produce bathochromic shifts, the red shift, and hypsochromic shift, the blue shift, by stabilizing either ground state or excited state. Finally, we learned to interpret spectra. We assigned absorption peaks to specific electron transitions. You categorized the transitions into sigma to sigma star, pi to pi star and n to pi star processes based on energy requirements and molar absorptivity. Take a moment to appreciate the scope of what you have accomplished. Together, these topics describe one fundamental question: what happens when energy enters a molecular system? Absorption spectroscopy is entirely about energy input. A photon arrives and the system absorbs it, but physics does not stop there. Accordingly to the laws of fundamental laws of thermodynamics, an excited quantum state is inherently unstable. A molecule cannot remain excited forever. Once an electron is promoted to a higher orbital, the system must eventually release that excess energy and return to thermal equilibrium. This requirement is unavoidable, and this physical necessity naturally leads us the second half of our syllabus. We now transition into molecular luminous spectroscopy. Here the perspective changes. Absorption spectroscopy measures the light removed from an incident beam. Luminescence spectroscopy, in contrast, measures new light generated by the sample itself. Instead of studying energy entering matter, we now study how matter releases energy. In the upcoming lectures, we will explore luminescence in crystal and molecular systems. We will carefully analyze excitation mechanisms, emission processes, and decay pathways. You will learn how excited states relax through specific quantum routes. A central theme will be understanding the difference between fluorescence and phosphorescence. We will not memorize definitions. Instead, we will construct energy level diagrams and analyze physics behind them. You will see how electron spin, selection rules, and intersystem crossing control emission behavior. We will also introduce a quantitative description of emission processes. You will learn how to define quantum efficiency, also called quantum yield, which measures how effectively absorbed energy is converted into emitted light. From theory, we will again move to instrumentation. We will study fluorometers and spectrofluorometers, specialized instruments designed to detect extremely weak emissions. These devices allows us to measure light produced by sample itself. Finally, we will enter the domain of time-resolved spectroscopy. Here, we measure how long excited states survive. You will learn to determine radiative lifetimes, natural lifetimes, and decay constant. We will analyze decay curves and understand how lifetime data reveals microscopic processes inside materials. So, today marks an important conceptual transition. Until now, we studied how matter receives energy. From this point forward, we study how matter dissipates energy. This shift from absorption to emission opens the door to some of the most powerful tools in modern physics, chemistry, and material science. So, let us now begin our journey into molecular luminescence spectroscopy. Thank you.